The Institute of Art Conservation and Colour was the first scientific laboratory of artworks in the private sector in the French market. The I.A.C.C. was established in 1979 by Sylvaine BRANS, a restorer accredited by the Louvre Museum and the Musées de France in 1964. In recent years, together with Nessir BRANS, the Institute designed and developed different types of analysis adapted to the field of art to determine the quality of artworks and a range of other information using an entirely scientific approach. This approach is coupled with expertise in the field of art restoration and over 40 years of in-depth knowledge of painting. Such a combination of expertise and experience is vital to a sound understanding of a scientific analysis. The laboratory enables us to analyse paintings for authentication purposes, helping our clients to avoid acquiring paintings of suspect origin. Expert scientific analysis of artworks. Our photographic laboratory enables us, by means of scientific investigation, to provide detailed information to bear on all questions relating to works of art. It caters for experts, collectors, dealers, restorers, and anyone keen to gain a better understanding of a particular work. The types of investigation possible include macrophotography, microphotography, chemical analysis of pigments, raking light photography, sodium light photography, ultraviolet radiation photography, infrared radiation photography, and radiography. Macrophotography is close-up photography of a detail magnified by the lens. It allows us to observe the painter's brushstroke by distinguishing between the impasto layers. It is a very precise reading to help us understanding a painter's work and an invaluable basis for comparison when we examine a painting for the purposes of identification. Chemical analysis and microsampling of pigments. Microphotography involves shooting a particular detail under a microscope with a 50 to 400 times magnification. First, it provides an image of the specific point to be examined. For example, after a microscopic examination, the technique either captures an image of the artist's own personal style, or it reveals an anomaly by highlighting the difference between the original material and material added to the work at a later date. In addition, the technique provides an image of a microsample strata, which means that before the possible destruction by chemical analysis of a microscopic sample of pictorial matter, we can capture the successive layers of the sample by photograph under a microscope. The objective of chemically analysing a sample is to identify the different pigments or binders that make up the pictorial layer. It is often in investigating an anachronism that evidence of forgery is uncovered. For example, the presence of a chemical element discovered only in the 19th century would provide conclusive evidence of forgery in a painting that appears, even in its technique, to be of a much earlier period. The physical and microchemical analysis of microsamples allows us to identify the different materials present, as well as the pigments and binders that make up the pictorial layer. In some cases, this analysis can be carried out by other non-destructive means without the need for samples, for example by using X-ray fluorescence. This analysis plays a role in authentication. In identifying a pigment or binder, we tie the work to a particular moment of creation. The process helps us to situate the artwork in time, as the chemical components of pigments and binders are generally characteristic of a particular era. It is often in investigating an anachronism that evidence of forgery is uncovered, and vice versa, the presence of pigments that are compatible with the period in which a painting was made can securely locate the work in a given era. To this end, various techniques, often complementary, can be used. Such techniques enable us to analyse paintings, but also polychrome sculpture, art on paper, and even the paper itself. Here are some examples of the most commonly used methods in the field of painting. For pigment analysis, there are several techniques we can use. To begin, we use an optical microscope for an overview of the colour point to be analysed. A sample is taken and examined on its outer surface, inner surface, and cross-section to see the stratigraphy, that is, the various successive layers of materials deposited from the preparatory layer to the final varnish. We then use scanning electron microscopy microanalysis on the sample. We have also, of course, the stratigraphic cross-section image, but the SEM analysis provides several other pieces of crucial information in addition to that provided by the image of the stratigraphy. The magnifying capabilities in this technique are such that we can see the shape of the material's particles, which are often characteristic of an era. For example, the pigment grinding technique may have been manual or mechanical, or of a particular chemical element. Using an EDX probe, SEM also produces a spectrum of all the chemical elements that it tracks. EDX provides qualitative and quantitative analysis of the elemental composition of a sample by using a diode to measure the X-ray photon energy emitted by the area of the sample bombarded by the electron beam. Next, X-ray fluorescence. This is an elemental analysis technique which, without touching the work or taking a sample through the use of X-ray, identifies the chemical elements of surface pigments. A very fine beam is projected onto the painting, allowing us to analyse the chemical elements of a specific colour point. The computer presents the results as spectra that are then examined to deduce the presence of pigments in the colour point analysed. This technique enables very fast analysis of the various colours present. It can provide preliminary results within just a few hours. Raman spectroscopic analysis is a structural analysis technique that allows us to identify the materials used in an artwork. It can be applied to samples or performed without samples. The technique can therefore be non-destructive if necessary. We use this analysis especially to distinguish between anatase and rutile titanium white, which can imply a dating gap of about 30 years. Raman analysis is also used for more precise research on the possible presence of copper in blues and greens, which, depending the form in which it is present, would mean different dates of production. But Raman analysis is also very useful for examining organic pigments which cannot be detected by X-ray fluorescence and for which SEM is not always effective. The result of the study is a spectrum which is then compared to other reference spectra of various known materials. To analyse binders, lacquers and adhesives, we also use several different techniques. The first is microchemical analysis, which, for example, in the case of binders, allows us to differentiate between a lipid-based binder, oil, and a protein-based binder, tempera. But if further detail is required, we use Fourier transform infrared spectroscopy, which, based on the measurement of the infrared light intensity absorbed by the sample, provides its structural characteristics as a spectrum, which is then compared with reference spectra. And this is how we identify the unknown material. A sample is necessary. It should be noted, however, that the sample size can be tiny. About the size of a pin head is needed for the analysis of a painting. We also conduct investigations on the paper. For this, we first observe the paper under a microscope. Then we use scanning electron microscopy. This allows us to distinguish between traditional cotton rag paper and more modern wood pulp paper. In addition, in the case of rag paper, we can distinguish between the types of fibres used, for example cotton or linen, which have very specific types of fibres. Then, through chemical analysis, we can identify the presence or absence of bleaching agents and, most importantly, determine their chemical nature in order to date the work. For example, kaolin has been used for a very long time, whereas synthetic optical brighteners only make an appearance in the 19th and 20th century. Now, to examine the canvas, the back of the artwork where the canvas is visible is scanned under a microscope. The twist of the flax, hemp or cotton yarn and the weave of threads are inspected for any contamination with plastic fibres. The plastic fibres might originate, for example, in synthetic binders, which serve to bond flax fibre bundles, or they can arise as a result of pollution. Such contamination is common after 1950 because of factors relating to the weaving process and in particular with regard to the supply of flax, hemp and cotton fibres from the power loom. Under the microscope, a plastic fibre can be clearly observed, its length, thickness and the profile of its cross-section. Raking or grazing light photography provides information on the topography of a painting and gives us a different view of the impasto effects as well as of any accidents or cracks. Photography under sodium light photography. Photography under sodium light photography can bring an additional element to the study of a painting. In abstracting the colour, we can see the best of the painting. The contrasts are emphasised, even more pronounced than in black and white, displaying the painter's technique, his brushstroke, his hand. Ultraviolet fluorescence photography. Ultraviolet photography is a first test to determine a painting's state of conservation. It shows up the location of accidents, any overpainting, the type of varnish used, and because of this, once the restoration process is complete, it can be compared to a photograph of the painting and used as a fact in any dispute. UV photography can reveal surface retouching as the overpainting on the varnish appears as dark patches, in contrast to the painting's original material. Some pigments can also be perceived abnormally in the rendering of values. For this reason, UV examination is a little more challenging than at first it may seem. It may be that a fluorescent substance was added to a recent varnish to camouflage several overpaintings, and therefore further tests are needed to provide more conclusive information on the real condition of the painting. Ultraviolet reflection photography. We must distinguish clearly between ultraviolet reflection photography and ultraviolet fluorescence photography. These are two very different but complementary techniques. Ultraviolet reflection photography brings out inscriptions, erasures, and barely visible components, but in a way that is quite different from infrared photography. The way the material is penetrated and the optical reaction of the pigments under UV rays are indeed not the same as under infrared rays. Black and white infrared photography. A property of infrared rays is that they have the ability to pass through the upper paint layers but not beyond. Infrared photography reveals accidents not detectable under ultraviolet light and has the capability to reach the preparatory drawing as well as potentially any hidden signatures or inscriptions. False colour infrared photography. A whole range of pigments can be identified with this technique. False colour infrared photography makes it possible to identify pigments optically. Each colour has a corresponding pigment type, but also enables us to differentiate between paint layers applied using different techniques or in different eras. It is sometimes necessary to photograph several palettes with colour samples in specific wavelengths with the same lighting and the same computer and camera settings in order to compare the results with the photographs of the paintings. These colour palettes will be used to compare and identify optically some of the components of the various pigments used by the painter. The technique of false colour photography is one of the fastest and most effective means of reaching a conclusion about the quality and authenticity of a work. Indeed, for every colour in false colour infrared type 1 or 2, there is a corresponding specific material or mixture of materials. We describe the chemical constituents of a pigment as materials. For example, 3 white pigments which look similar to the naked eye, meaning that they have the same visible appearance but are of different chemical composition, will have 3 very different colours in false colour infrared. Thus, we can visually identify the material's constituents when we have points of reference, palettes of different pigments, or a reference work to make the comparison. We look for the similarities or the inconsistencies in colour between the photos of the palettes and those of the paintings in a group of corresponding wavelengths. If all visible colours have the same colour correspondence in both pictures, whether it is in false colour infrared type 1 or 2, then this means that the pigments used are very similar, even identical, and mixed together in similar proportions. X-ray of artworks. Radiography. If we want to see beyond the preparatory layer of the painting, we can get more information from an X-ray picture. Radiography shows the exact condition of a painting without the need for any sort of intervention on the pictorial layer. In addition, the technique provides information about the wood, or canvas support, stamps on the back, fastening nails and filling materials. It can give us insight into certain internal structures or the artist's hesitation, known in French as repentir. Finally, and most spectacularly, the technique can reveal the presence of a hidden painting underneath. Radiography can be used to create an authentic archive document for the holder in case of theft or loss. For this reason, the image should accompany any certificate of authenticity. Art restoration. All of these investigations are necessary in order to establish a record, which is the first stage of the research and assessment process. They are also necessary and indispensable to the restorer of artworks, who must first understand the various issues to be addressed and then handle them in the best way possible. Our restoration and recanvassing workshops, which are led by a restorer with accreditations from the Louvre Museum and the Musées de France, are equipped to completely handle all the specific instances that arise relating to, among others, varnish removal processes and removal of overpainting, filling material and retouch. As it ages, the protective varnish brings a distinctly yellowish hue to the picture, which does not reflect the painting's original appearance. We must remove the varnish but without damaging the paint layer, making this a very delicate operation. In the past, restorations did not always abide by the drawings or the styles of the painting. Indeed, they often contributed to an anarchical transformation of the painting. Look closely at this picture. You can see that the upper part is blue in colour. It is an overpaint. It was concealing a whole pale pink sky, as you can see it uncovered in the lower part of the painting. Once the layers of overpaint are removed, accidents or cracks may be exposed, which we must then fill to bring them to the level of the paint layer ready for retouching. This painting of David has been completely transformed by a poor restoration which altered the painter's drawing and style. When the overpaint is lifted, these major accidents are exposed. Sealants will fill the gaps, and this time the retouching will endeavour to respect the painter's drawing and style. Our distinctive retouching technique, which we developed with the help of colour scientists, depends on the use of 3-colour synthesis. It prevents premature aging of the paint typically used in restoration. Your eye, like mine, reconstructs a colour from 3 elements that we call primary. With the help of 3 coloured dots selected and placed on the sealant, it will use additive colour synthesis to recreate the desired colour. To enable professionals and private individuals to acquire or deepen their knowledge in this field, the I.A.C.C has set up professional training courses in 2 areas: Techniques for the Scientific Analysis of Artworks, 1 10-hour module, and Painting Restoration Techniques, 9 modules, total time of 94 hours and 30 minutes. The I.A.C.C is state recognised, which provides access to funding for professional training. The courses are aimed primarily at those with foundational knowledge in the field of art, but we also offer an introductory training to anyone interested in knowing more about scientific analysis and art restoration. The training can be done individually or as a group, maximum 5 people at a reduced cost. Information on our training programmes is available on our website www.iacc.fr. If you wish to invest in art, we place our skills at your disposal to help you bring your plans to life. As noted, our company in Paris is specialised in the field of art since 1979 and has extensive experience to offer, including artwork restoration, artwork analysis, art expertise and sales. Our laboratory can analyse paintings for authentication purposes and so that our customers avoid acquiring paintings of suspect origin. Few companies can offer such complementary skills. Apart from the many artworks with whose restoration our clients entrust us and the scientific expertise from which they benefit, some of these clients also ask us to assist with the sale of their works. We therefore have at hand paintings by modern masters, impressionists and old masters, high quality works and, importantly, handled confidentially. Please do not hesitate to contact us. We are at your disposal. We are available at 014800476 or 0608177511 if you wish to make an appointment. If you are calling from outside France, please dial +33 148 000476 or +33 608 177511. We look forward to welcoming you at our studio in Paris at 15 Rue Grange Batelier 75009. We can also travel to you, either elsewhere in France or abroad, according to your needs. For further information, please visit our website www.iacc.com.